Okay, rather than grading and answering in class about this AP practice problem that I handed out, I'm just going to do this video recording so you can kind of watch the details whenever you want. I picked this question because it involves stuff really throughout the whole year and shows how we're going to have to use and remember all the pieces from previous terms and sections to describe things even now we're in the simple harmonic motion part. So, part A gives us two boxes, right? The box of capital M, the larger mass, and the box of little m, the smaller mass. And the little mass is hanging from a rope, and the larger mass is on a table connected to a rope and a spring. So, we're asked to just label all the forces. And there's actually a lot of flexibility in how you want to do this. When I see label all the forces, I think of variable names like tension or weight or whatever it might be. So that's what I'm going to do. However, as part B and C will make us do, we're going to need numbers for these things anyway. So if, as you're doing this, you instead of writing the force of gravity, when we get to that, you write, well, I know it's 8 kilograms and G is 9.8. You actually write that mg product value. That would be fine too. That would suffice. So I'm going to label them with variables. If you did it with numbers, as long as the numbers are right, that's fine. So the block of mass big M has a rope, so a tension force. It has a spring, so I'm going to call it force spring. It's sitting on a table, so there's a normal force. And there's also the weight, capital Mg. Right, so 4 forces. We're told the table is frictionless, so we don't have any of that. And the little m mass has the same rope attached to it, so there's a tension, and it has a weight as well, so little mg. Right, and it's not sitting on any surface, there's no springs, nothing else, so it's just those two forces. So that's part A. And part A, everyone, I hope, should get. You have to be able to sort of set up and organize what's going on. So part B, we have to calculate the tension in the string. So we have a couple different ways that we could think about this, but hopefully the first thing that comes to mind is that you have both objects have the tension force in them, but one of them is really a lot simpler, right? That one only has 2 forces. So we're going to write Newton's second law for that little mass m, and since the forces are all vertical, I'm going to write the vertical part of Newton's second law. And we're told that it's in equilibrium. That means it's not accelerating. Specifically in this case, it's also not moving, but the key is it's not accelerating. So this equals 0. So we have a vertical upward force, the tension, and a vertical downward force, little mg, and that has to equal 0. So this tells us that the tension equals mg, which is 4 kilograms times 9.8 meters per second squared, or 39 newtons, right? Now, part C is similar, but a couple more steps. So we know what the tension is, and we're told that the string is massless. So that tells us that the tension that is holding up the little block and the tension that's attached to the big block have to be the same. And we're still in equilibrium. So I'm going to write for the larger block, capital M, the horizontal equilibrium, because we care about the spring force, which is a horizontal force. So the sum of the horizontal forces is capital MA, but it's in equilibrium, so that equals 0 still. We have 2 horizontal forces. Tension is in the positive direction. The spring force is in the negative. Oops, I don't want to write that. Spring force is in the negative direction. So that equals 0. But we know how to write the spring force, and I've already assigned the direction, right, with this negative sign. Right, this negative sign is what's indicated direction. So I don't need to worry about the negative in the restoring force, because that negative just tells me it's opposite the direction the spring is stretched, which I've already done by putting that negative sign in there. So tension equals the spring force, which we know is Kx. So all we need to do is figure out how much the spring is stretched, and we're told that its unstretched length is 20 meters, or 0.2 meters, and its length when hanging when this equilibrium setup is 0.25 meters. So that means x is 0.25 minus 0.20, or 0.05 meters. That's how much it's stretched, which is what we need for that. So k is t over x is 39 divided by 0.05, or 780 newtons per meter. Okay? And again, you have to get the units, newtons per meter. All right, so that answers parts A, B, and C, which are like chapters 4 and 5 sorts of stuff, right? Free body diagrams, forces, equilibrium statements, Newton's laws. But we have a couple other parts. Right now we're told the string is now cut at point P, and we need to figure out how long it takes the 4-kilogram block to hit the floor. So if the string is cut, the 4-kilogram block is in free fall. And so this is a kinematics question, right? Because I'm asking about time. There are many different ways you could go about solving this. You could use energy conservation to figure out the speed the block hits the ground at, and then use that final speed and the initial speed at rest to calculate time using kinematics. But that's kind of inefficient. Really the fastest way is just to use a kinematics equation that relates the distance you travel to your initial velocity, your acceleration, and the time taken. And so if you look up that one, right, it's going to be this. Right, that one's on the AP sheet in various forms. The initial velocity, however, starts at rest, so that's 0. That makes that term easy. And so delta y, well actually I'm going to rearrange with variables first. We're trying to solve for delta t, right? So 2 delta y over a equals delta t squared. And so if I take the square root of both sides, right, I get what delta t is. So now I just have to figure out what goes in those number spots. So the 2 is good. Delta y is a negative number, right? It's going down. And specifically it goes down negative 0.7 meters. And a, the acceleration, it's in free fall. Again, it's a negative because it's g, but downward. So negative 9.8 meters per second squared. And that gives us the amount of time that it takes to hit the ground, which if you plug all that into your calculator should give you 0.38 seconds. So part D is a kinematics thing. That's like chapters 1 through 3. Now we actually get to the simple harmonic stuff, parts E and F. So the frequency of oscillation of the 3-kilogram block. Well, we know that the frequency, or the period, only depends on the mass that's oscillating and the spring constant. We found the spring constant in part C, and we're given the mass in the problem. That's all we need. So you're given the period on the AP equation sheet, but if you get the period, just do 1 over that and you get the frequency, or you can invert the equation for frequency, which is what I'm going to do. Either way. So the frequency, 1 over 2 pi square root of k over m. And that equation, once you identify what you're trying to do, is pretty easy to solve because we have k and m. So you plug in the k is 780, you plug in m, right, this actually should be capital M, right, because it's the big mass, is 8 kilograms, and you get a number of 1.6. And since it's a frequency, that has units of hertz, so 1.6 hertz. So this one, once you remember that all you need is the mass and the spring constant, is a pretty fast step. And then finally, part F, the maximum speed. So this was one where you're not given the equation that we've used in class directly. If you remember it, great. If not, the easiest way to get the maximum speed is to do a conservation of energy sort of process. So we know that the maximum speed happens when it's in equilibrium and all the energy is kinetic. but it's easier to describe the maximum energy in terms of the maximum stretch length of the spring, right? And since energy is conserved, there's no friction, there's nothing else that we're assuming would be lost, we can say that the energy that the spring has when it's stretched at equilibrium, 1/2 k, stretched as far as it is possible away from equilibrium, which is the amplitude, right, 1/2 k a squared, that's the spring energy, must equal the maximum kinetic energy that it can get, 1/2 capital M, V max squared, right? This is saying that energy is conserved, basically. So if we can figure out the amplitude, right, we can solve this because we still have the mass and we still have the spring constant. So we know that the spring is stretched 5 centimeters or 0.05 meters right before the string is cut. So that tells us that the maximum amount of stretch of the spring is that same 0.5 meters or 0.05 meters. That's our amplitude. Right, so this is 0.05. This is 8 kilograms, and this is 780 newtons per meter. And now I can see that I can solve pretty easily for that. So the 1/2s will cancel. Right? If I rearrange, I'll solve that V max squared equals K over M A squared, right? Or V max equals the square root of K over M times A, right? And we have all these numbers. So I just plug it in, and I get that the maximum speed is 0.49 meters per second. The other way to do this is if you just remembered V max equals 2 pi F A, which is an equation we've used, but it's not on the sheet. If you remember that, we have the frequency, right? That was what we did before, and then the amplitude is that same value. And if you plug that in, you'll get the same answer. So there's multiple ways you can solve this, but the way I did it doesn't require you to have anything memorized, right? So that's how you solve this one, and it uses a lot of different pieces, so you kind of have to be prepared for that on the AP test or exams here.